What if we could actually listen to the Earth breathe? Track every single inhale and exhale of carbon dioxide from forests, grasslands, all over the world. This constant exchange of carbon between the land and the air, well, it's a vital sign for our planet's health. And getting an accurate reading is one of the single biggest challenges in climate science today. Okay, so to get those readings, we rely on these special sensors called Flux towers. But as you can probably tell from this map, our eyes on the ground are, well, they're pretty few and far between. We've got these dense clusters in North America and Europe, but then these huge blind spots across Africa, South America, and Asia. It's kind of like trying to understand the health of the entire planet by only looking at a few specific neighborhoods.
And that leads us to the central question we're tackling today. With a dataset that's so patchy, so incomplete, how in the world do scientists fill in all those blanks to create a full, high-res map of the Earth's carbon cycle? It's a massive puzzle, and it's going to take more than just connecting a few dots.
So let's really dig into this challenge. What does it mean to have only a partial view, and why is it so incredibly important that we fix it? Here's the bottom line. Tracking these carbon fluxes is absolutely essential. We're talking about things like gross primary production, or GPP. Think of that as the total amount of CO2 plants breathe in. And then there's net ecosystem exchange, or NEE, which is kind of the final score, the balance of carbon going in versus carbon going out. These numbers are the bedrock of our climate models. If we get them wrong, our predictions are wrong. But if we get them right, we can make much, much smarter decisions. So the scientific name for solving this puzzle is upscaling. It's all about taking that sparse data and blowing it up into a global picture. And as we're about to see, it's a whole lot trickier than it sounds. Upscaling basically means taking the limited, ground-level truth from those towers, mashing it up with global satellite images, and then trying to guess what's happening everywhere else. Imagine trying to create a perfect, high-definition map of the entire planet, but your only source material is a handful of tourist photos from a few scattered cities. Yeah, that's the challenge. And this is where it gets really tricky. You just can't use a one-size-fits-all formula. The relationship between what a satellite sees, like how green a landscape is, and how much carbon is actually being exchanged, is totally different in a rainforest than it is in a savanna. They follow different rules, they speak a different local dialect, and the older methods, well, they just couldn't keep up with that local context. So if the old methods are hitting a wall, what's the solution? Well, this brings us to the hero of our story, a new AI framework that's basically designed to be a detective, one that's capable of learning all these different local rules. Researchers at the University of Minnesota developed a framework with a bit of a mouthful of a name, Task-Aware Modulation with Representation Learning. So for the rest of this, we're just going to call it by its much friendlier acronym, TAMRL. Okay, I know this diagram looks incredibly complicated. All the boxes, all the arrows, but don't worry about it. The real genius of TAMRL is actually in its clever two-part design, and we can explain it with a really simple analogy. Think of TAMRL as a master linguist. When it arrives at a new location, it doesn't just start talking. First, it listens. It analyzes all the unique local data, the climate, the soil, everything, to learn its local dialect. Only after it understands that specific context does it then modulate or adjust its core model so that it becomes fluent in that location's specific carbon language. It's custom-tailored, not one-size-fits-all. So what's its secret sauce? Well, first, there's that amazing ability to learn local context. Second, and this is huge, it's not just some black box guessing at patterns. It has a fundamental law of physics built right into its logic, the carbon balance equation. This means its answers have to be scientifically plausible. And third, it's designed for what's called zero-shot generalization. This is a wild AI ability to make accurate predictions for places it has never seen before, not even once. That right there is the key to filling in those global blind spots. The theory sounds incredible, right? But talk is cheap. How does this new AI actually perform when you put it in the ring against the current best model out there? Let's get to the head-to-head challenge. In this corner, we have the challenger, our new AI detective, TAMRL. And in the other corner, the reigning champion and the current state-of-the-art model, a system called FluxCom X-Space. And the results are pretty clear. In these charts, a lower bar means less error, so lower is better. The teal bar, that's our challenger, TAMRL. The dark green is the reigning champ. Just look across the different ecosystems and climates. Almost without exception, that teal bar is consistently lower. TAMRL is just more accurate. Let's put some hard numbers on that win. For estimating gross primary production, again, that's the total carbon absorbed by plants, TAMRL reduced the overall error by nearly 10%. That's a huge improvement over the best we had before. But here is the truly stunning result. For net ecosystem exchange, that critical bottom line of whether an ecosystem is a carbon sink or a source, TAMRL delivered a nearly 44% improvement in accuracy. Let that sink in. 44%. That's not just a step up, it's a massive leap forward. And we can see this dominance on a site-by-site basis. In the chart on the left, any dot below the diagonal line is a win for TAMRL, meaning less error. On the right, any dot above the line is a win, showing higher accuracy. The trend is just undeniable. The vast majority of sites fall squarely in TAMRL's favor. Okay, so the AI is a better number cruncher. It wins the technical challenge hands down. But let's connect this back to the big picture. Why does this specific breakthrough really matter for all of us? It creates this really powerful and direct chain of impact. This new AI gives us fundamentally better carbon maps of the world. Those more accurate maps get fed into our global climate models, making them significantly more reliable. And when our models are more reliable, our leaders and scientists can make much smarter, better informed decisions for the future of the planet. The research authors themselves put it best, saying that this work can substantially enhance the robustness and transferability of global carbon flux estimates, which, in plain English, means our ability to map Earth's carbon cycle just took a major step forward. Now, this isn't a silver bullet, not yet. The researchers are very clear that challenges are still out there. The model still has some trouble with certain ecosystems, especially things like wetlands and some specific types of forests. The hunt for an even clearer picture is definitely still on, but the path forward just got a whole lot brighter. And all of this brings us to our final thought. Technologies like TAMRL are giving us a powerful new lens, an ever clearer, more detailed picture of how our planet actually works. So the crucial question this progress leaves us with is a really profound one. As we start to see our world with this newfound clarity, what will we choose to do with what we see?